Hello and welcome to Equity Education, the chemistry version. And today we're going to be looking at relative atomic mass, so how to calculate relative atomic mass from certain data. We're going to have a bit of background on the use of carbon-12 and then we'll do some calculations. Should be a quick video today. Okay, so I need to open up your booklet and we will get started. Okay, right, so some background information. So we say the use of carbon-12. What is carbon-12? So there are about 1.673 times 10 to the 23 molecules in one drop of water. And to count these molecules individually would be nearly impossible. Therefore, atoms and molecules are counted by their mass. This is possible because all atoms of different elements have different masses. For this to work, all atoms of elements need to be measured against something. The standard atom of reference is, you will be unsurprised to hear, carbon-12. Okay, so I'd like you to calculate the number of subatomic particles in carbon-12, which should only take you a minute. Okay, as you've probably worked out, I didn't give you the atomic number, so you had to find that off the periodic table. So our atomic number is 6, so we have 6 protons. We must have 6 electrons because it's a neutral atom. 12 minus 6 to get our number of neutrons, so 6, 6, 6. Okay, so to make it easier, an atom of carbon-12 is said to weigh exactly 12 mass units. That's given the symbol U. And the atomic mass units in carbon-12 is roughly equal to the number of protons and neutrons in one atom of carbon-12. This means that one U atomic unit is roughly equal to 1 proton or 1 neutron. So that's just a bit of background information, okay? And it will start to make a bit more sense, this piece of information, when we come on to the next page. Okay, so moving down, so you have to know these definitions, you have to remember them off by heart. So let's go through them. So relative isotopic mass is the mass of an atom of an isotope relative to 1/12 the mass of an atom of carbon-12. Relative atomic mass, which you may see as RAN, is the weighted mean mass of an atom of an element. Let's fill that out. I've left a gap there, I have. Of an element relative to 1/12 the mass of carbon-12. Okay, moving on. So relative molecular mass, which you may see as RMM, I haven't left enough space here, is the weighted mean mass of a molecule relative to, have a guess what this is, 1/12 the mass of carbon-12, and relative formula mass, which you might see as RFM. I think I'm just going to write these at the top, so this is RMM, and this is RFM, and this is RAM. Okay, so relative formula mass is, unsurprisingly, the weighted mean mass of a formula unit of a compound relative to, you've guessed it, 1/12 the mass of carbon-12. Okay, so you have to know these definitions off by heart. Okay, so moving on. Right, so when do we use these? When do we use these phrases and definitions? Relative molecular mass is used when the smallest unit is a molecule. E.g., CO2, H2O, methane, for example. So these are all molecules. Relative formula unit is used when the smallest unit is a formula unit of an ionic compound, e.g. sodium chloride, magnesium chloride. Let's choose another one. Let's do lithium fluoride. Okay, so technically, when you're calculating molecular mass or formula unit, the definition depends on whether it's a molecule or an ionic compound. However, if you look in chemistry books or on the web, half the time relative formula unit isn't used, rather it's just referred to as relative molecular mass. Strictly speaking, it should be relative formula unit. However, if you see calculate relative molecular mass for an ionic compound, you just do it. Okay? Right, so moving on. Okay, so why this 1/12 of carbon? Why just 1/12 of carbon? So it is important to include the phrase 1/12 when describing relative masses. The reason being that it doesn't make sense otherwise. So, a bit of explanation. So we know that 1 U atomic unit is equal to roughly the mass of 1 proton or 1 neutron. This means that we are effectively measuring the mass of 1 neutron or proton against the mass of 1 atom of an element. And that sort of makes sense. So if we look at the mass number of carbon, we know it's 12. So 1/12 would be 1. And we know that there's 12 protons and neutrons in carbon. Therefore, that's where we get this 1/12 from. Okay, for example then, so e.g. hydrogen has how many protons? It has 1 proton. If we measured it compared to 1/12 of carbon 12, which would roughly equal 1 U, it is equal to 1. Yeah, so we're comparing hydrogen with proton to 1 atomic unit, therefore we should expect a value of 1 on the periodic table this is, and the atomic number of hydrogen, the mass number of hydrogen is 1. Okay. So I just noticed I made a mistake in my booklet here, so the MR of hydrogen is 1, and that's what we see on the periodic table. Okay, so some another good examples. So helium has 2 protons and 2 neutrons. If I compare it to 1/12 of carbon 12, which again is 1 atomic unit, it is roughly how many times as big? Got 2 protons, got 2 neutrons, so I have 4 in total. It is roughly 4 times as big. Therefore, the MR of helium on the periodic table should be 4, which it is. So that's what we mean when we're explaining, when we're comparing it to 1/12 of carbon 12. We're comparing it to 1/12, not the whole of carbon 12. And that's where we get these MRs from on the periodic table. Right, so explaining the definitions. This is a bit wordy, but the example on the next page, the calculation should make it make a bit more sense. So, relative isotopic mass does not contain the words weighted mean mass. And this is because we are comparing 1 atom of an isotope directly with 1/12 of a carbon 12. E.g., magnesium has some isotopes, so we'll take magnesium 24. So when we're calculating the relative isotopic mass, I'm comparing this 1 atom of magnesium directly with 1/12 of carbon 12. Okay, so relative atomic mass, formula mass, and molecular mass all contain the phrase weighted mean mass. And this is because most elements have isotopes. Isotopes are, we'll do the definition, are atoms of the same element with the same number of protons but different number of neutrons. So this means that isotopes of elements have different mass numbers because they may have more neutrons or less neutrons. So when we are comparing these different isotopes with 1/12 of carbon-12, we have to take these masses into account, so all of the masses of the isotopes, and compare them with 1/12 of carbon-12. E.g., I'll just do it quickly here. So if we have magnesium isotopes, we have magnesium-24, and I have magnesium-25. So magnesium-25 has one more neutron, and I'm comparing both of these with 1/12 of carbon-12 when I'm talking about relative atomic mass. Okay, so moving on. So to complicate matters, different isotopes of an element occur in different abundances Oh, that's not how you spell abundances. Let's try again. Naturally in the environment. Okay, so in the Earth's crust, we'll have all of these different elements. Yeah, and they occur naturally. The isotopes of these elements occur naturally in different amounts. Abundances really means amounts. E.g., so chlorine has two isotopes, 35Cl and 37Cl. It naturally occurs in abundances of 75% for 35Cl and 25% for 37Cl. Technically it should be 75.5 and 24.5, but I've rounded it up, as you'll see why. Okay, so therefore if there was 100 molecules of chlorine in a jar, how many molecules of each isotope would there be? So that you have to think about it and read through that question again. Okay, well obviously then we would have 75 of the chlorine 35 isotope and 25 of the chlorine 37. Okay, next question. Okay, I'd like you to have a go at it. How would you calculate the mass of all of the 100 molecules in the jar? Well, if we're calculating this mass, the mass of these, we would obviously do 75 times by 35 plus 25 times by 37. So I've taken the amount, I've times it by the mass number, and I've taken this amount and times it by the mass number, which gives us a value of, we have to do the calculation, 75 times by 35 plus 25 times by 37, oops, 75 times by 35 plus 25 times by 37 equals, well, I could have worked that out in my head, 3,550. So 3,550. Okay. Next question. How would you calculate the average mass of the chlorine molecules in the jar? Again, I'll let you think about it, do the calculation. Okay, well, I'm sure you've worked it out. That I would have to take my total mass, which is 3,550, and I need to divide it by the total number of molecules in the jar, which is 100. So that gives me a value of 35.5 for the average mass of one chlorine molecule in that jar. Okay, so why have we done that? We've done that because this is basically how we calculate the relative atomic mass of an element. So to calculate the relative atomic mass of an element, we use this formula. So the sum of the mass of an isotope times by the abundance of the isotope. And if we're using percentage abundances, which you probably will be in the exams, so it should be divide. We divide by 100. Sorry, my computer's playing up. Right, so this is the formula that you need to remember. So to calculate relative atomic mass, we do the sum of the mass of an isotope times by the abundance of the isotope divided by 100. And I will just write this here. So this means sum of. Right, so your turn. So calculate the relative atomic mass of magnesium to 3 significant figures, given that the 3 naturally occurring isotopes of magnesium, 24, 25 and 26, have percentage abundances of 79, 10% and 11%. Okay, I'll give you a couple of minutes. Okay, so I'm sure you've been able to work this out, so I've just written out my formula again. So I'm going to take the mass of an isotope, so I'll take the mass, the first one, which is 24, times by its abundance, which is 79, plus the mass of my next isotope, which is 25, times by its abundance, which is 10, plus the mass of the last isotope, times by its abundance, 11, and I'm going to divide by 100, and that gives me a value of 24.32. If you notice in the question, as to 3 significant figures, so let's round this to 24.3. Okay, right, so moving on. Read through this question, then I'll say something before you have a go at the calculation. So, sample of rubidium contains 3.61 times 10 to the 23 atoms of 85 Rb and 1.39 times 10 to the 23 atoms of 87 Rb. Calculate the relative atomic mass of Rb in the sample to 3 significant figures. Okay, so before you start, we don't have percentages here. We don't have percentages. So what do you think we're going to divide by? Okay, right, have a think, have a go at the calculation, and we'll see what you get. Okay, and I'm sure you've worked this out. Oh, let me just change this slightly. So in this example, we don't have percentage abundances. However, we do have number of molecules, number of atoms. See, I just wrote molecules instead of atoms as well. So to calculate this, we need to, again, use the mass of an isotope times by the number of atoms of the isotope and divide by the total number of atoms in the sample. And this is because it's not a percentage abundance, okay? So I'm sure you got this right, so we'll just go through the answer. So the mass of isotope here is 85 times by the number of molecules, so 3.61 times 10 to the 23, plus my mass, my next isotope, 87, times by 1.39 times 10 to the 23, and I'm going to divide by my total number of atoms in the sample. So I add up my 3.61 times 10 to the 23 with 1.39 times 10 to the 23, which is 5 times 10 to the 23, which gives me a value of 85.556. It says the 3 significant figures, so therefore 85.6 is my answer. Okay, right, I'm sure you got that right, and we'll move on to probably the hardest type of question you can be asked about calculating relative atomic mass. I'll read through it and then I'll give you a few more minutes for this one because it is quite tricky. So boron exists as two isotopes, 10B and 11B. Given the relative atomic mass of boron is 10.8, what are the percentage abundances of the two isotopes? Okay, now I'm going to give you a clue. So we know that it's a percentage abundance, and we know that there's two isotopes. So therefore, my percentage abundance of 10B plus my percentage abundance of 11B must equal 100. Right, so that's my clue. See if you can calculate this and I'll go through it with you in a minute. Okay, right, so tricky or not? So we know that if we have two isotopes, the percentage abundance must equal 100. Therefore, I know that one abundance must equal 100 minus x, and the other abundance must equal x. Yeah? So we have to do a bit of algebra here. So I know that the relative atomic mass is 10.8. So I know that to calculate, we'll just go back up here. We're going to be using this formula again. So my mass of the isotope is equal to 10. And I don't have a percentage abundance, but I do know that I can calculate it using this, so 100 minus x. So 100 minus x. Plus, again, I'm going to have my mass of my isotope, which I have, times by x, because that will be my other abundance. I'm dividing by 100 because it's a percentage abundance, and then I need to do some calculations. So I need to expand these brackets. So 10 times 100 is 1000 minus 10x plus 11x over 100 equals 10.8. Therefore, I would have, what will I have? 1080 equals 1000. I'll simplify this to plus x. Therefore, x, I minus my 1000 from this, is equal to 80. So x is equal to 80. This x must be my percentage abundance of my mass of boron 11. So therefore, 11 has a percentage abundance of 80%. And 100 minus x gets me my other percentage abundance. So 100 minus 80 equals 20. So therefore it's 20%. Okay, so a bit of maths involved in that one. And you can have a check to make sure it's right by, well, having a rough guess. So we know that the relative atomic mass here is 10.8. So therefore, we would think that there will be more of the 11 isotope compared to the 10 because it's closer to 11 than it is to 10. And that works out. So we have 10.8. Right, and do we want to say anything else? Oh yeah, one last thing before I go. So we'll use this in an example. So here we got a value of 85.6, and that makes sense because it's between 85 and 87, which are our two isotopes of rubidium. If I got any value which isn't between 85 and 87, so 2, 1000, then obviously know that you've done the calculation wrong. Something has gone wrong. So that's a quick tip that you can use to make sure that your answer is correct. Okay, it's been short and sweet, this video today, and I hope it was useful, and I will see you next time. Okay, bye bye.